I will discuss today the maximum collector efficiency for class A operation. Class A power amplifier. So this is transistor NPN. Collector is attached to VCC with a resistor RC. Emitter is grounded. Here is a resistor RC. And the supply is given to base also through RB. Input signal is applied to the base through a capacitor. So this is a power transistor. Because the efficiency of this circuit is very low, so it is seldom used for power amplification, but even then we are studying it because to learn about the power relation used in the circuit. Okay? Now we are coming to the expression for collector efficiency. Efficiency by definition, it is always output upon input. But of course here, what is the output? That is AC signal, AC power output. There's output, input is DC power, which is used for getting the AC power. Okay? So small PO upon PDC, PO mean output power. DC power is what? It is because of the power supply VCC multiplied by IC. IC is the average value of the output current. VC is the collector supply voltage. IC is the average value of the collector current. Fine? Okay. Now what is the output AC power? That is the varying collector ammeter voltage VCE multiplied by IC. IC mean the varying collector current, and moreover there the RMS values for the output AC power. The RMS value of the varying signals are used here. RMS voltage multiplied by RMS current. RMS mean root mean square. Let this a signal which is varying. Now peak to peak value. VCE peak to peak, and it is converted to the RMS now. How? First of all, it is taken as half mean amplitude part, half divided by root 2 becomes RMS. So half of this divided by root 2 becomes RMS value of the voltage. This becomes RMS value. That becomes VCE upon 2 root 2. Remember, VCE is small VCE lowercase. That's a peak to peak value. Similarly, the RMS value of the current, that's a peak to peak current divided by 2 root 2. Now the collector efficiency is output power upon the input power. So this is the relation of efficiency, and it is used now in the next part. This relation will be used. Now we are going to draw a graph between the collector current, varying current, and varying collector ammeter voltage. This is a DC load line, black one. Let me draw some parallel lines like this. This is the Q point. The middle point of the load line is Q point. The yellow lines corresponding to Q point. Here the collector ammeter voltage is varying like this, with the result collector current will vary like this. Now collector ammeter varying like in this fashion, and collector current like this way. This is a Q point. This value is VCC. This is half of VCC. This is 0. Now current is voltage over resistance, so VCC by RL. This is half of the current. VCC, not RL, RC, sorry. VCC over RC is IC, maximum IC. Now what is maximum value of VCE? Look, 0 reference and VCC. That becomes VCC only. Maximum value of current, you look, 0 is the reference level, then VCC by RC. So maximum value of the varying current, maximum value of the varying current means peak to peak, I mean to say. These values are peak to peak, the voltage and current. Now using the maximum AC output power, what will be? Using the above relation which we just derived, that is the peak to peak voltage and peak to peak current divided by 8, that is the output power, 8 RC. Okay, VCC square by 8 RC, and DC power is VCC into IC. IC is the average value of the collector current, which is you look here, the average value is VCC by 2RC. This is the average value, the yellow line. Okay, this is capital I and small c. So substituting the average value of the current, which is VCC by 2RC, so that becomes VCC square upon 2RC. So we are having output power, we are having DC power. Now we find the efficiency. Maximum collector efficiency, denoted with eta, becomes output power over the input power. So it becomes only 25%, very, very less. This is the theoretical value, and the experimental value or the practical value will be even less. So this is the reason that this class A operation is very rarely used. Now we look what is the maximum collector efficiency if at the collector side a transformer coupling is used. So instead of using directly the RC or the load resistance, if we used a transformer there at the collector side, so if transformer coupling is used, it permits the impedance transformer used because impedance matching first of all. Now the question is, why are we using the transformer at the load side? Because the impedance matching. Number 2, it keeps the DC power loss small because of small resistance of the primary of the transformer windings. Transformer primary winding, the resistance is very, very small, especially the DC resistance is negligible exactly, because they are the coils, and DC resistance, we assume that it is 0. And when no signal is applied to the circuit, then what happens? Then the effective resistance to the collector is that of the primary winding, and primary winding having negligible resistance, so there is no resistance at the collector for no signal. That means 0 resistance mean infinite current. With the voltage, there is a voltage and infinite current because of the 0 resistance. So DC load line, so DC load line will be a straight line parallel to the y-axis. It's a vertical line rising from the VCC parallel to the y-axis, where what is y? The current. So this is a yellow line, dotted one. So VCC and DC load line. This is because with no signal, there is no resistance of the primary winding then. Now the circuit is like this: common ammeter configuration. There is a ammeter resistor, bypass capacitor, base terminal, and potential divider arrangement for biasing. Capacitor signal is sent to the base to capacitor. Then here is a coil, primary turns of the transformer, VCC supply, and iron core, then secondary windings, and at the secondary winding there is a load resistance RL. So this is the circuit basically. Now in order to get the maximum AC output power, what is requirement? It is that the peak value of the collector current due to signal alone should be equal to zero signal collector current IC. This is a very important condition. You know what the mean of this condition. So I think we to redraw this graph, sorry. So we cross it and we again draw the graph. And we also see what was that condition which I just mentioned above. This is a yellow line. This is AC load line, not DC load line. This is the DC load line. This is AC load line because with the signal. Okay, the center point, the Q point. Here the parallel lines parallel to the this is again the parallel lines, okay, to the signal. So here the value of VCC, here the value of IC. Now the collector current varies like this between IC and 2IC. This reference level below it is 0. So collector current, that means varying peak to peak 0 to 2IC, and with the result VCC varies like this. VCE is varying like this. So collector current varying, VCE is varying. So look, this is 2 VCC, this is 0 reference level. So Q point is the middle. Now collector ammeter voltage swing is, twice the VCC, and total swing of the collector current twice of the IC. we need for output power peak to peak collector emitter voltage, that is twice VCC, and peak to peak collector current, that is twice IC. So again, because IC is what voltage over resistance, resistance is RL dash, because it includes the transformer reactances also. So DC power is I square R, mean I square RL dash. Maximum AC output power is already we derived this relation above, that it is peak to peak values of voltage and current divided by 8. And substituting the peak to peak values, peak to peak value of voltage and current substituting, okay, that becomes AC, maximum AC output power. Now this is here 1 by 2. Now we find the this is maximum AC power. Now we find maximum collector efficiency with transformer. Output power upon the input power. Input power is DC power. So substituting the value of AC output power calculated just above divided by DC power I square RL dash. Now RL dash cancels out and efficiency becomes 50% with transformer. This is good attempt. That 50% of the DC supply is converted into the useful AC power output. Practically, the efficiency will be somewhat less than 50%, but even then it is good. So, because of the power losses, so what is the power dissipation by the transformer? This is power loss is DC power minus the AC power, because whatever the difference is, that is lost. So now one thing more, if suppose there is no input signal, that is there is a zero signal, then the losses will be equals to the DC power. So DC power is actually the loss. The loss is okay. Thank you very much for watching my video. Please subscribe my channel also. Okay. I will discuss today the maximum collector efficiency for class A operation.